Hello ladies and gentlemen, welcome back to the other video. So this time we're going to be looking at Newton's laws, that is Newton's laws of motion. And here are the notes. I think I have them open already. So yes, we have now Newton's laws. Let me just open this one. Okay, so making it bigger. So this is your chapter 2. Chapter 2. Okay, so looking at Newton's laws, that is particle dynamics. So this is particle dynamics. Now we're interested in what is causing the motion. At first in kinematics we're just interested in the motion itself, but now we're interested in what is causing the motion as well. So this is why we look at dynamics, and the main part of it is just the Newton's laws of motion. So the following 3 laws of motion, just like you did obviously in the first year of study, the same laws are just repeating in the same or maybe rather slightly different way. So the following 3 laws of motion are given by Sir Isaac Newton, are considered the axioms of mechanics. They are considered the makeup of mechanics. So the first law of motion states that every particle persists in a state of rest or of uniform motion in a straight line unless acted upon by a force. Okay, I'm sure this is something you already know as the law of inertia. A particle will remain at rest, or if it is moving, it will continue in its initial state of motion unless it is acted upon by an external force. That's the first law of motion. Okay, so that's what we are saying. And the second law of motion just states if F is the force acting on a particle of mass m, which as a consequence is moving with velocity v, then force is equal to the time derivative of the product of mass and velocity, which is just dp over dt. Because mv here is just momentum, of course momentum is a vector, it has a direction, and velocity is a vector. So force is just dp over dt. And when you look at this, where mv, which is p, is just called the momentum, if m is independent of time t, this becomes force is equal to m dv over dt. So this is in a case where the mass is constant. Mass is constant, it is independent of time. So we can factor it out and make it dv over dt. So we know that dv over dt is just acceleration. Hence we're having what is called force equals ma. So this is the Newton's second law, which just states that force is equal to the product of mass and acceleration. So as you can see here, it's written where a is the acceleration of the particle. So that's the second law of motion. Now the third law of motion just states that if particle 1 acts on particle 2, okay, so imagine you have 2 particles. If particle 1 is acting on particle 2 with a force F12 in a direction along the line joining the particles, while particle 2 acts on particle 1, okay, with a force F21, then F21 is equal to minus F12. Okay, so this means that these particles will have the same force but opposite in direction. These particles will have the same force but opposite in direction. In other words, to every action there is an equal and opposite reaction. That's how you state Newton's third law. For every action there is an equal and opposite reaction. I'll give an example of this. Imagine you are hammering a nail into a piece of wood. If you use that hammer, the force on the hammer will be hitting the nail. But as you hit the nail with your hammer, you will feel a rebound in your hand, which is the force from the nail as it collides with the hammer. So that force is opposing the force from the hammer. So that's why I was saying that for every action there's an equal but opposite reaction. In other words, you can also say that the more you hammer that nail into the piece of wood, the more force you use, the more rebound effect you're going to experience in your hand because of the force which is opposing the force from the hammer. And that force opposing the force from the hammer is the force which is coming from the nail as you hit it. Okay, to be opposing that force. So there's always an equal but opposite reaction. So that's a quick definition of the Newton's second law, third law. So now let's look at definitions of force and mass. Well, mass is just defined as the quantity of matter in a substance. Of course, mass is just the quantity of matter in a substance. And force is just simply um, a vector which is uh, points in some direction. Force can just be defined as the pull of gravity acting. If it is weight, you can define it as the pull of gravity acting on an object. So a force is just something which causes an acceleration on an object. Anything that you push or a pull that causes an acceleration on an object. Okay, so yeah, let's look at weight and acceleration due to gravity. Weight and acceleration due to gravity. It is found experimentally that the Earth's surface objects fall with a vertical acceleration. Okay, so it is found experimentally that near the Earth's surface, okay, so this word is near the Earth's surface, objects fall with a vertical acceleration which is constant, provided that air resistance is negligible. Okay, so this is constant provided that air resistance is negligible. Okay, now this acceleration is denoted by g, and we all know that that is the force of gravity, and it is called the acceleration due to gravity or gravitational acceleration. And the approximate magnitude of g is just 9.8 meters per second squared on the Earth. So this gravity varies from one place to another. Like on the moon, it is about 6 meters per second squared, or even much less than that. So on the moon, it is much less than on the Earth. All right. And in outer space, there is no gravity. I'm sure you've seen an astronaut in space just floating in a free space there. Okay, they float because there is no gravity up there. Now, assuming that the surface of the Earth is represented by the XY plane of figure 2.2, so that has to be 2.2. The force acting on a particle of mass m is given by, okay, the force acting on the particle is given by weight equals mass mg k hat. So this is a particle which is in space, right? The only force which will be acting on it is gravity. Okay, so this is us assuming that the surface of the Earth is represented by the XY plane. So this is the particle we're looking at, this one, in figure 2.2. So this has to be 2.2, not 3.2. You see this particle, the only force acting on it, it's in free space. The only force that will act on it is the gravity, which is minus mg. We know that we have to get the weight, we must multiply the mass and the gravity. And the negative sign just shows that gravity acts in the opposite direction as we have chosen the positive axis. So in this diagram, up is chosen as positive, upward motion is chosen as positive, meaning that every vector that points up is positive, every vector that points down is negative. That's why it is a negative there. That's why this weight is given as minus mg k hat. K hat is just showing the direction, meaning that it is in the vertical axis there, which is the z-axis. Now, this force, which is called the weight of the particle, has magnitude mg. Of course, that's just the magnitude. We neglect the direction because we're just looking at the magnitude of this force here, which is just mass times gravity. Of course, you know that magnitude is a scalar. That's why we're not interested in the direction. Okay, so that is something about a particle which is in free space. Now, looking at freely falling bodies. Freely falling bodies. If an object moves so that the only force acting on it is the weight or the force due to gravity, then the object is called a freely falling body. Okay, as long as it is moving such that the only force acting on it is the force of gravity, then that object is a freely falling body. Now, if r, this is vector r, is the position vector and m is the mass of the body, then using Newton's second law, the differential equation of motion is seen from equation 2.3 to be m d2r over dt squared is equal to minus mg k hat. Okay, so this is just second law here. We know force is equal to ma. This m here is the mass. d2r over dt squared is just the acceleration. This is something which we've done before. The second derivative of position gives the acceleration, which is equal to minus mg k hat. Mg k hat, now this is the force, which is what we found here, minus mg k hat. So this is a freely falling body. The only force acting on it is gravity, which is minus mg k hat. K hat, that's the direction, meaning that it is in the k hat axis, or with respect to the k hat basis vector. Or the 2r over the t squared is equal to minus g k hat. So now that is, if you cancel out the m here and cancels out with that m there, you get this expression. Now, since this equation does not involve the mass m, the motion of a freely falling body is independent of its mass. Okay, so I'll repeat, since this equation does not involve the mass, okay, this equation here, it does not involve the mass in it, the motion of a freely falling body is independent of its mass. All right, so we are going to look at examples on how we can handle questions concerning these laws or these equations which we're just explaining. Okay, so now we can look at motion in a resisting medium. Motion in a resisting medium. So in practice, an object is not only acted upon by its weight, but by other forces as well, of course. Now, such forces which generally arise because of motion in some medium, such as air or water, are often called resisting, damping, or dissipative forces. So any forces which are opposing the motion of an object are called resisting forces, or you can call them damping forces or dissipative forces. Now, it is found experimentally that for low speeds, the resisting force is in a magnitude proportional to the speed. Okay, the resisting force is proportional to the speed. What do we mean here? Imagine you're speeding a car. The amount of resistance or the wind resistance which will be faced by the windscreen on your car will increase as you speed up that car. It will increase as you speed up that car, meaning that you are increasing the force on the car, the forward force on the car as it increases. Even the wind resistance will increase on the windshield of your car. So that is speed. The more speed you give to the car, the more resisting force you experience. That's just an example to explain this statement. Now, if the resisting force is R, okay, that's R, resisting force, then the motion a particle of mass m in an otherwise uniform force field is given by, okay, so this is an object which is obviously in a resistant medium, which is falling freely and being resisted by some maybe air resistance. So this is m d2r over dt squared is equal to minus, or rather is equal to mg k hat minus r. Okay, so this is equal to mg k hat minus r. So r is that resisting force. So this is an example of motion in a resisting medium. Okay. Of course, if an object is falling freely, there has to be a minus here. Okay, there has to be a minus here, um, and okay, it just depends. If you want to choose up positive or negative, we'll have this kind of expression here. So according to this equation here, what was chosen positive is down. Down was chosen positive from this equation. As you can see, this mgk hat is positive. It is positive because down was chosen positive, the direction of motion. It was chosen positive here, and the minus r here just means that up was chosen negative because the resisting force will obviously be acting upwards on this particle. Okay, so don't get confused here. I'll explain more on what is happening. But all in all, on this particular equation, what I'm saying is that down was chosen positive. That's why this gravity, this pull of gravity here is having what sign? It is having a, a positive sign because this is an example of a particle which is just falling freely. So here down was chosen positive. And when an object is falling in the air, the only resistance which will be acting on it is air resistance. Now that air resistance, where will it act on the body? It will be acting upwards. Air resistance will be acting upwards. That's why it is negative here. So I'll state this again for the second time. For this particular equation, down was chosen positive and up negative. Okay. Yeah, we'll look at an example on motion in a resisting medium. Okay, now let's look at constrained motion. In some cases, a particle P must move along some specified curve or surface, as for example the inclined plane of figure 3.3 or the inner surface of a hemispherical ball in figure 3.4. So any surface along which an object is moving is called a constraint, and that's what you call constrained motion. So this is a particle P moving on an incline. As it moves, it will experience some forces on it. Of course, this is a particle moving freely to experience a friction force there, a normal force, and the weight. Of course, this incline is at an angle of alpha, and of course, this other particle, of course, is moving on a curved surface like that. So in our notes, we'll just focus on Newton's laws and resistant forces with motion. Now, for this case here, on constrained motion, we're saying that such a curve or surface on which the particle must move is called a constraint, and the resistant motion is called constrained motion. So the surface along which the particle moves is called a constraint, and the motion is called constrained motion. Just as the particle exerts a force on the constraint, there will by Newton's third law be a reaction force on the constraint. Okay. Now this reaction force is often um, given in terms of components like Newton. This is the normal, of course, as you can see here. For this first diagram, this figure 3.3, we have the normal force acting upwards and the weight downwards, the friction, of course, acting upwards. Okay, all right, so now let's see what we can do or what problems we can solve for this kind of case. But before we do that, let's finish up here. We're saying that this reaction force is often described by giving its components N and F normal to and parallel to the direction of motion respectively. So N is normal to and F is parallel to the direction of motion. Okay, now in most cases which arise in practice, F is the force due to friction and is taken in a direction opposing motion. So this type of F is just representing friction. As you can see here, there's F there, friction, this F friction, because this particle will be going down the incline. Even here, this particle will be going down the curve. That's why we're getting a friction which is tangent to that part. Okay, so enough of the talking. Let's see the next video. I'll look at problems to do with particle dynamics.